Hello and welcome. In this video, I'll be working through an example of orbital velocity. The question reads, a spacecraft is to be put into a circular orbit about a spherical planet. The planet may be considered to be isolated in space. The mass of the planet, assumed to be concentrated at its center, is 7.5 times 10 to the 23 kilograms. The radius of the planet is 3.4 by 10 to the 6 meters. The spacecraft is to orbit the planet at a height of 2.4 by 10 to the 5 meters above the surface of the planet. At this altitude, there is no atmosphere. So that's saying there's no drag forces to slow it down. We only have to we don't have to consider any force besides gravity, right? And which is providing the centripetal force to keep it in a circular orbit. Show that the speed is this. We could say, show that the orbital velocity is this, right? So they're giving us the answer based on this data, and we've got to be able to sort of show that this is the correct orbital velocity for a given altitude. Some of you might have it memorized that orbital velocity is the square root of g(m) over r. But where does that come from? It comes from ideas about circular motion. So the centripetal force is equal to mass times centripetal acceleration. And centripetal acceleration is velocity squared over r. So this is centripetal force. We equate it to Newton's law of universal gravitation, cancel out what we can, and that's where this comes from. So we should be able to solve for a velocity, get an answer, and then see if it's this number. G has a value of 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. That's G. The mass of the planet being orbited, given here, 7.5 by 10 to the 23 kilograms. And then R might be helpful to draw a picture. So we've got a planet that has a certain radius, and we've got the spacecraft, and this is not to scale, the spacecraft, draw my best spaceship here. I'll make it look like an airplane, kind of futuristic, cool, like that. All right, here's my spaceship. All right, so it's a certain distance also. So we basically need to add the radius of the planet to the height, and you can see that this is about it's a whole order of magnitude sort of less than it. So it's basically, just sort of this, but let's be complete here. So R is the distance from the center of the planet that the object is, right? So it's the separation distance. It's separated not just from the surface, but from the entire planet, right? They give us permission by saying the mass can be concentrated at its center, this far away from the surface. So the total distance is 3.4 by 10 to the 6 meters plus 2.4 by 10 to the 5 meters. So we want to add those two. 3.6 by 10 to the 6 is 3.4. 3.4 by 10 to the 6 meters is 3.4 million meters. Add to that 2.4 by 10 to the 5 meters, that's 240,000 meters. And that gives us 3.64 by 10 to the 6 meters. Okay. So, yeah, this 4 and this 2, right? Because this is an order of magnitude, so this 2 gets added to this 4. That's where the 6 comes from. That 4 stays up. That makes sense. All right, and so that goes in the denominator down here. So this kilogram squared just comes from the units of G. Down here in the denominator with those kilogram squared units is this distance, 3.64 by 10 to the 6 meters. If we look at what all the units do, like this meter will cancel out one of those. This kilogram cancels out one of these, and we get newtons. Newton meters, right? There's still a meter up here, Newton meter per kilogram. So a Newton meter per kilogram, I'm going to write this off to the side, it should give us meters squared per second squared, because once we take the square root of these units, it's got to give us meters per second, right? We're sort of restricted to that. So this is just a quick check to make sure this should work out, right? A Newton is a kilogram meter per second squared because of Newton's second law. This one right here tells us that a Newton of force is equal to a kilogram of mass times a meter per second squared of acceleration. So that's just the base units of a Newton, the derived unit, are kilogram meters per second squared. So this is a Newton. Still got this meter out here, so meters are squared. This kilogram down here cancels that. And indeed, underneath the radical, the units we've got are meters squared per second squared. So once we take the square root of these units, we'll get meters per second of velocity. So that's a nice little check, just make sure, okay, the units work. So that builds our confidence we're on the right track. Crunch those numbers there. So you got 6.67 by 10 to the negative 11 times 7.5 by 10 to the 23 divided by 3.64 by 10 to the 6. And then take the square root of all of that. You can take a square root by just raising something to the 1/2 power. That's the same thing as taking a square root. So sometimes it's easier to type it in your calculator that way. All right, so I'm getting 6.67 times 10 to the negative 11 times 7.5 by 10 to the 23 divided by, open parentheses, 3.64, and I got to start over. 6.67 by 10 to the negative 11 times 7.5 by 10 to the 23 divided by, open parentheses, 3.64. Calculator, you get the decimal point last time, times 10 to the 6, close parentheses, equals. So now I've got the answer under the radical. And you go, well, that's faster than the speed of light. Oh, yeah, still got to take the square root. So I get, does anybody have the calculator value here? Because remember, we know the answer is this. So don't just say 3.7 by 10 to the 3. We know it's that. What does it actually say in the calculator when you do this? Anybody got it? I'll give you some adequate wait time here. All right, that's long enough. I forgot that we're recording here. A lot of just time. You should get 3707. All right, 3707. So that's, and it's like there's more, 0.17, whatever. And that is indeed about this. 3707 is about 3.7 by 10 to the 3 meters per second. It all checks out. We've shown that the speed of that spacecraft at that distance has to be 3.7 by 10 to the 3.